So my name is Filippo, I work for Art Research, and when I received the invitation to come and talk, I had a great idea in mind. I talk about computing and more, post-more, heterogeneity, new materials, how you design a chip, what kind of constraint you have when you do this kind of design exploration. Then I realized that the talk would take probably an hour, and then I realized I had only 15 minutes. So I had to chunk the topic to one specific that we've been heavily working in the team in Cambridge, and also we believe it's relevant for some of the activity that DiRAC developer will do possibly in the future in collaboration with an initiative called Catalyst that we have with our partner, Marvel, HP, so on and so forth. And but a lot of the activity we do that are more forward-looking on the technology side, because as you know, in the way, hopefully I don't have to go through that, because I skipped that slide. The art business model, we really don't build the final product. We enable others to build product on top of it. So we're like an IP provider. It's our core research activity that touch HPC, has been touching HPC so far and will continue in the future around this concept of co-design. So this is slide 0, then there is a title. But I wanted to bring it up because it's important, because we feel proud of working very closely with application developers around this co-design idea, because sometimes what we're looking at doesn't yet exist. So we have to build tool, method, methodology, and somehow understanding how this would behave if it actually become a real product in the future. So for this specific talk, I focus on one key element, that is one key feature that we hope to see in many products from many of our partners, that is the Scalar vector extension. And I will go through what is SVE a little bit about, what is SVE today, how does it work, what methodology we build to exploit it, and to give an idea of application developer what feature can bring it, but then a little bit slightly, very fast talk about the future, what's come next, maybe in the future. So I think everybody is more or less familiar with how SIMD work. Okay, if you have a normal Scalar processor, one element, or in single, if you have a vector processor, or some vector capabilities in your CPU, you have a chunk of 4, chunk of 4, chunk of 4. If your loop is not a multiplier of 4, the tail of the loop has somehow to be handled serially or with tricks. We developed this extension of our instruction set called Scalar vector extension, when you have two key concepts. One is around the concept of predicate that allow you to mask access to vector unit in a way that by issuing the same instruction to just compute the data that you really need. And the other one is that it doesn't fix the vector map, meaning that when you buy anything today that has vector capability, you buy 256, 512, 1024. When we start to survey around what's the right one, well, there's no right one. And sadly, some applications exploit vectorization better than others for multiple reasons. Let's not go down, because that's another probably hour of topic. But the reality is that there's a lot of effort put in compiler, library, runtimes that allow to exploit vectorization properly. And there's a lot of assumption in this piece of software about what's the best vector length, which again is not the best for everybody. So we went this idea of a Scalar vector extension. It is a generic HISA that allows, in principle, a hardware implementation of whatever length between 128 to 248. But if you look at the assembly, there's no clear indication that you're processing 512 or 256. It's done in a way that when it's hardware implemented by anyone who wants it, it uses it. From an assembly perspective, is essentially transparent. So we believe this is a good approach to enable more vectorization, because it handles a lot of corner cases, and we also believe that by doing that, we can add more speculative opportunities for compiler to auto-vectorize the code, because we have to admit that vectorized code is still a hard topic. SVE also bring other new elements like scatter gather and predicate and horizontal reduction. Let's not go through that. My idea was really about try to having this SVE part. And SVE, as a feature, in the way hardware design every feature for the processor, is an optional feature that can go into a CPU that a partner produces. So if you, today you're going to look at, okay, I want to try it in hardware, what I can buy, or what I can actually use to have a feeling about how good it is. Well, ARM cannot really give you that, because with design specification, someone else is going to build the CPU. We already know that one is coming, we may not mention that, but a part of that is in the hand of other people. So internally, in order to understand if it's good and how to be improved, we designed some open source tool and some methodology that allow to essentially experiment in a field if with that hardware capabilities, your specific software, it's good or bad, or if it's bad, what can be changed in software, or eventually in hardware, if you are a CPU hardware, in order to run it faster. So I will mention related to the present of SVE, I will mention about emulation and what the real hardware exists. I will skip the simulation part, because the simulation part it's long to explain. But the key difference between simulation and emulation is that emulation will just, without being cycle accurate, so it doesn't really run like a real CPU, you emulate a functionality that is coded in an instruction. A simulator will actually simulate in a different box the capability of a specific hardware feature. And usually simulator is way more slower. Simulators are the main tool to use to design CPU today, but it's not always possible to run a big simulation code into a simulator, because it will take like years, something that takes 10 seconds. Emulator, it's a completely different approach. So we developed, and again, this is open, it doesn't need a license, it can be downloaded. One runs with multiple compilers, for as long as they compile code with ARM instruction set. But we developed this emulator with the idea that with this piece of tool, you have your own code, you compile this code with this new capability, you pass through the emulator tells you it runs correctly, and gives you interesting statistics about how this application is behaving on that hardware component. And some 64-bit, and the key element I would say is that it's based on a code, it's based on a package called DynamoRio that does binary instrumentation. It's a piece of software that's, again, free, developed by Google, I guess, mainly, that allows you to take any instruction your current program is executed on CPU and do whatever you want, from rewriting, they use it for security things, like rewriting or changing the address completely. It's very flexible. But we're using this to emulate the instructions that are not yet present in hardware. So if you have the fortune of trying one of the DiRAC system, actually they run an hackathon on this system, the catalyst machine, you will have an ARM system, you can run your code and that's great. But there's no real vector capability apart of Neo. This is coming from previous generation, 32-bit, mobile, area. So if you add this new feature, because this feature may come in the future and you want to be ready for it, your computer is going to tell you wrong, it's a legal instruction, you don't understand it, and it stops. If you put ARM in front of it, it will tell you, oh great, it gives the answer, 142, whatever it is. Obviously, he has to emulate the instruction, so it's going to be slightly slower, so it's not for performance in terms of time to solution, but at least allow you to check that everything works well. What is interesting is that when you get the CPU, it will have a specific fixed vector length, a specific fixed number of vector instructions, a vector length instruction. So, for example, 512. Now, what if I have double of it, or more of it? So, the emulator allows you to basically tune this hardware feature and try again more and more. Obviously, having a piece of tool that tells you, okay, the answer is correct, and just run is kind of useless. What we can do about it. So because within ARM, we design CPU understanding how our ISA and our system EP affect computing down the line, so for the next generation product, we build, especially for high-performance computing code, on top of ARM, a series of what we call instrument, this we call it instruments, we call it like a client. I don't know what's the exact name, but the idea is that it's like a module, it's actually a module that anyone can customize that does a specific things. So for example, allow you, once your application runs, to count how many vector instructions you issue, what type of vector instruction you issue, how much vector you're using, how you are not using it. And that's become from an instruction set point of view. But if you're also looking at the memory, because you have to move memory in and out, it tells you how much the data is sparse, or what kind of access pattern you have. Because sometimes one of the limits of vectorization that prevent achieving peak is that you can't feed your vector units enough. So maybe you have the right length, but guess what? You don't have enough bandwidth to the cache level to feed this vector unit accordingly and keep them always busy. This can help basically to develop a methodology that allows you to say, okay, it's potentially good to vectorize, but it's still poor. How is my memory access pattern? Can I change it? What is the effect of it? And so on and so forth. And we developed, as I say, different clients, one for instruction, one for memory. And we developed this methodology. We actually using this to optimize several benchmarks, several subset of code, not entirely code, subset of code, because obviously we don't, this is only about the compute part. So if there is networking, there is I/O, this is beyond this element. But the compute inside, the compute kernel, we look at many of them on different domains. And now we're also focusing on, obviously, what is deep learning and analytics. But the idea is that take the application, you just compile it. you extract some key metrics, then you check if all these instruction and memory are utilized, and then you apply change into the code. You can also run another one of these internal, one of these additional modular client, a sort of cache simulator. I'm limited by cache, by accessing the cache, by latency, things like that. And based on that, you come out with what can we call it between brackets an optimal solution. It's an application that maybe is not super optimal for that specific hardware because the specific hardware does not exist yet. But once the hardware arrives, you're essentially ready for it. This is what we want to do. So the hardware exists. So this is a news that is on public. There will be an hardware, a big machine, exascale scale in Japan called Fugaku. There will be a system, a CPU capable of SVE, and is on the headline everywhere in the HPC world. This is great. But that machine is custom. It's a custom network, custom storage, it's custom everything. What is important, because I think it's going to touch a little bit the life of, say, people outside that community, is that that chip is going to be made available in a more commodity-like setting. And I like this for two reasons. One is that, I mean, there will be a vendor, and it's all public. You can check this talk by the guy in Storybrooke and the Brookhaven Laboratory, which basically advertised this, that has, willingness to put in a different boxes to broaden the ecosystem. But they made a choice of having this system with this capability because they claim that on exceed workload, 86% of the cycle stay in 32 gigabytes of memory. So the average, this is bizarre, this is interesting, they claim that the average, based on the average job size, okay, that they are running, you divide by the number of nodes, they notice that the majority of the cycle do not consume the full 32 gigabytes. And because this chip has 32 gigabytes of HBM, they say this will be useful for this community. It's a very diverse community. They do material science, molecular dynamics, cosmology as well. It will be very interesting to see when this machine comes live if this assumption is true. I guess one of the key elements here is that it's very important that we have more and more capacity on our node in terms of memory. But if a code is scalable, you can always overcome this problem to a certain degree. But anyway, this is interesting to see that also outside Japan, this kind of technology will click up. What comes next? So this is normal vectorization, and it's happening in a normal CPU server like. What we know is that the way compute working, we call it compute continuum, is changing a little bit. And the idea is that people are still doing computation at the data center, HPC people and HPC people as well, but computing at the edge, computing at the IoT is becoming more and more pervasive. Your car will be able to do more compute than the HPC system 10 years ago. Your mobile phone is already more powerful probably than a single laptop or a single workstation in certain degree. But all these devices, they can leverage the capabilities of vectorization. So we extended our SVE with the idea of, what's called SVE2, with the idea to extend more instruction that allow fixed point calculation or image processing, signal processing specifically for this domain, because this is where you find computer vision, AR, VR, bioinformatics, or networking. You've been tested the blue field, for example. This is one of the cases where, our IP is applied for in-network computing, but is also very important because you can offload computation to that free your CPU to do something else. And let's keep on the feature. Another element that we started to add, because more and more parallelism has to be exposed from an application point of view, is transactional memory. Transactional memory, in short, is you replace a critical section in a multi-threaded application with a transaction. So you open a transaction, you do some operation. When you close a transaction, so you have to make a commit on memory. If there's no conflict in the way memory has been accessed, then your computation is essentially written in memory efficiently. It's very interesting because maybe from an HPC point of view, this doesn't seem very mind-blowing, but imagine a database. You have multiple clients reading a database. Sometimes people write. You want to make sure that all these concurrent access happen at the same time, and there is serialization only if you really touch the same shared memory area. Most of the time, might never happen. So transactional memory, obviously, it's not something we knew, exists for quite a while, but get it right and bundle with all the capability may actually help to increase parallelism. So in ARM, other than the problem that our partner are putting on the market, we'll try to basically push the boundary about what's possible to do with computing and what's possible to do to standard CPU processor. And SVE, SVE2, and TME are a couple of key technologies that we would like to see in the future going mainstream, but also be adopted as a way of optimizing in order to explore more parallelism. One is more about data level parallelism, the other one is more about thread level parallelism. But essentially, combined together will be able to deliver great performance. And what's very important is that these technologies that we are putting there are already in the open source, in the ecosystem, so open source tool can be developed on top of those, but they are not yet tied to any specific product that we will sell to our clients.